we continue with our study of basic algorithm design techniques. Let me restate three important techniques which will drive us. Okay, the three of them are: first one is induction. Okay, then ordering. Ordering the input, and the third is storing old values. Okay, so let me sort of let's talk about all these three once more. Induction essentially says, supposing you can solve the problem for smaller inputs, okay, how do you solve it for larger inputs? Okay, so this is the first design principle. So supposing you can put together these solutions for these smaller inputs and somehow generate a solution for the larger input, then your algorithm is clear. You sort of recurse on these smaller inputs, solve them, and when you get the solutions back, you put them together and get a solution to the larger input. Okay, that's induction. You could use either recursion, or it could even be, once you know what the smaller inputs are, it could even be iteration. Okay, the next point is ordering the input, which is you look at the input in some order. Okay, for instance, if it's an array, you look at it, let's say, in increasing order of indices. For other structures, it could be different. If it's a list, again, you will have to look at it element by element. For other input and other data structures, you could, this could vary. The other thing is store values which you may use later on. Okay, if you're not going to use a value which you've computed later on, then you can of course discard it. Otherwise, this very simple principle will help us design algorithms in the future. Okay, good. So we've seen some algorithms, simple algorithms for simple problems using these. The paradigm that we considered last time was divide and conquer. Okay. So the basic idea was this: if I have an input, let's say an array, but it could be absolutely anything, divide it into two parts. Okay, solve for the left, solve for the right, say. Okay, and then put the solution back together. Okay, so you divide input, now solve each part and put them together to get a solution for the big problem. Okay, and well, often it pays to divide it into equal parts. Okay, we'll in fact soon see an example why this is so. But even in the previous cases, for instance, max-min or finding the second minimum, the two examples that we saw, you could try breaking the input up into unequal pieces. Okay, and then try and solve the recurrence and see what answer you get. Okay, so you should I sort of encourage you to try this out. So the next problem we're going to consider is very familiar, should be very familiar to all of us. It's sorting. Okay, only we are going to look at it now from the new sort of design principles that we have learned, and we are going to try and apply this to sorting. Okay, so let's take the simplest sort of case. So you have an array. Okay, an array of n elements, and you would like to sort the elements in increasing order. Okay, let's assume that elements are distinct. This is not going to change any of our design principles or the algorithm we come up with, but it will just it is just to keep your mind less cluttered. Okay, so okay, so you have an array of, let's say, n elements, and you would like to sort them in increasing order. Let's put the first design principle into practice. Supposing you can solve it for a smaller array, how do you extend it to a bigger array? Okay, and the most natural smaller arrays, let's say the first n minus 1 elements. Okay, supposing I could solve this problem of sorting the array for the first n minus 1 elements, how do I now extend it to the bigger array? Okay, so here's the problem. Here's what the input looks like. This is the first n minus 1 elements, and this is the last element. Okay. Okay, so you first sort this. This is by recursion, let's say, and now I want to place this in the right position. Okay. Now, I guess most of you know binary search by now, so the position is very easily identified. Okay, so let's say this is now sorted. So this portion is sorted, and this position now is identified. Let's say there. You do a binary search and identify exactly where this goes in. Well, now what you have to do is to insert this in the right position, you have to move. You have to essentially make space. So from this point onwards, okay, you need to move everything one step to the right. Every element here you have to move one step to the right. Okay, move one step. And then insert the element in the right order. So here is an algorithm, right? So let's go over this again. You recursively sort the first n minus 1 elements, figure out where the last element sits in, and then put it in place. Okay, this is called insertion sort. So in your previous courses, you have dealt with this algorithm, right? You have learned insertion sort. There people, I guess, told you what insertion sort is all about. Here we are trying to understand how it is that people come up with these algorithms, okay? So that when you are faced with a new problem, you can come up with an algorithm of your own. That's the idea. Good. So this is how you come up with an insertion sort. It's just putting the principle we had into practice. Okay, how much time does this take? Well, if you just look at number of comparisons, okay, if I just want to find out the number of comparisons, the last element you used, the number of comparisons is log n, right, because you're doing a binary search. So, and every other element used like less time, right? It was, for the ith element it was log I, the time taken was log I. So the total time is in fact roughly order log n, order n log n. I mean, it's order log n per element. So there are n elements, and it's n log n. Okay. Yeah, but the main step here, which takes time, is not comparison, but this movement. Okay, let's look at the last step. The last step says, once I find this place, I have to move everything to the right. Now this place could actually be the beginning of the array, in which case you're going to shift the entire array by 1. Okay, so while you just took log n time to find the place, to move elements you may take n units of time. Okay, this is the expensive step in insertion sort, and if implemented in this manner, each time you take order n steps. Okay, for the ith step you take I units of time to move it to the right. You may take I units in the worst case, in which case the time will be order n squared. Okay, so I will leave it for you to see if you can use better data structures so that you can sort of avoid this movement. But implemented this way, insertion sort takes order n square time. Okay, though the number of comparisons here is still n log n. Let's put our other design paradigms into practice. Okay, so one was to divide the array equally. Okay, work on each piece and then put them together. Okay, let's look at this. So here's my sorting. So this is the second algorithm we are going to try. So here's my array. You divide it into two equal halves. Okay. Sort each piece. Okay, sort each piece, and then you have to put these things together. So let's write this down. So divide into two pieces. Sort each piece, and then put them together. Okay, so the algorithm is clear, right? Except for this step. What does it mean to put them together? So far it's okay. Dividing into two pieces, no sweat. Sort each recursion. Okay, you recurse on each piece, you sort each. Well, here is the crucial step that we need to implement, which is putting two sorted arrays together. Let me also say that this you could work with other data structures. Instead of arrays, you could have lists. Okay, and you can apply the same design principles to lists too. In fact, we will do this with arrays, but it really doesn't matter. Okay, so when I mention array, you could put a list there equally well. Okay, especially for this method. Okay, so we divide into two pieces. We sort each of them, okay, by recursion, and then we put the solutions together. What does this step entail? Well, this let's focus on this step, because once we implement this, the algorithm is ready, right, and you can program it at your leisure. Okay, so this step entails the following. I have two sorted arrays. Okay, sorted. I need to combine this to get one big sorted array. This is what I want. I have these two pieces which are sorted. Okay, this piece is sorted, so is that piece. We need to put these two sorted pieces together to get a big sorted piece. Okay, so this is the problem that we would like to solve. Okay, so this is called merging two sorted arrays or lists, it doesn't matter. Okay, so we are given elements. Okay, these are sorting, let's say, sorted in ascending order, and I would like to build a bigger structure which contains elements in both of them and which is sorted. Okay, so I guess the procedure should be fairly natural, and most of you should have gotten this by now, which is, well, what is the smallest? So here is my new list or array. Okay, this is my output. Which element will occupy the first position? Well, it has to be the smaller of these two elements, right? So what I do, I first compare the first elements of these two lists or arrays or sub arrays, okay, and put the smaller of them here. So I can have two pointers, okay, or two temporary variables which point to some places in the array. I compare these two, put the smaller one here, and move that corresponding pointer. Okay, let's call this A and that B. Supposing A1 is smaller than B1, then C of 1 I should assign the smaller of the two, which is A1, okay, right, and I should move this pointer. Okay, so let's call these two pointers something. So small a and small b. So small c is small a, and then I need to increment a. So increment. So a which is pointing here will point to the next element, and so on. So I just keep doing this at any stage. Okay, so what is the generic step? At some stage I have these arrays a and b. Okay, I have pointers small a and small b, and then I have pointer small c. I compare these two elements, put the smaller of them here, and increment the corresponding pointer. This is the algorithm. Okay, so I just essentially somehow scan these two and keep filling in these elements in this big array. Okay, so this is merging. I hope you can write code if need be. Okay, the idea is very simple, and if they are less, of course it's trivial. You have these two pointers, you sort of compare these two values, put the new value in a new list, okay, and increment these pointers. That's the way it's done. In arrays, if you want to, you may actually have sub-arrays of the original array where you're doing this work. You could have a temporary array where you create this merge list and then write it back into the original array. Okay. So this is the algorithm. So the merge step is also now done. This is the algorithm. How much time does this take? This algorithm is called merge sort, by the way. Okay, so it's called merge sort. And how much time does this take? Okay, let's go back to this the scribble piece of paper. So here is merge sort. It says divide into two pieces, sort each of them, then put them together. This is essentially merging two sorted sequences into one big sequence. Okay, that's the third step. Okay, so the divide step, well, doesn't take any time. Okay, sorting each is a recursive step. Okay, we sort on roughly half the array, and we need to figure out how much time does it take to put these things together. Good. So what's the time taken? Supposing Tn is the time for an array of size n, time for array of size n. Okay, by time again we'll focus on the number of comparisons, because even here every other operation, okay, is big O of number of comparisons. So if I can bound the number of comparisons, the total time is a constant times the number of comparisons. So please check this. Okay, for instance, moving the pointer, etc., etc., etc. Okay, and if you have lists, copying one list to the other, etc., they are all bounded by the number of comparisons. So I can just focus on this one quantity, which is number of comparisons. Okay. So let Tn be the number of comparisons that we make. We would now like to bound the total number of comparisons needed for an array of size n. Well, the divide step doesn't take any time. Okay, so but there are two sub problems of roughly equal size. Okay, so that gives you 2t n by 2. Again, we'll not worry about floors and ceilings, okay, for ease of calculation. And then there is a merge step. How much time does merge step take on an array of size n? Good. So this is something we need to do. Okay. So what is the merge step on an array of size n? Okay. So merge. I have two arrays of size n by 2. Okay, two sub arrays of size n by 2, or two lists of size n by 2, and I merge these to get something of size n. How much time does this take? Okay. Well, there are many ways of figuring this out. Okay. So let me tell you one way of doing it. Okay, this is a smart way of doing it, and then I'll tell you a way which is just using we'll again design this algorithm using design principles that we've already followed, and then analyze it that way also. Okay, so we'll do it two ways. Okay, so what is each step? Each step you compare two elements and an element gets filled in the array C, right? The crucial sort of observation here is that each time you make a comparison, okay, one element in C in this new array, the final sorted array, gets filled. Okay, once again, for each comparison, an extra element, a new element gets filled in the total array, right? How many elements get filled? The total number of elements that get filled into the new array is n. So the total number of comparisons you make is at most n. Okay, let me state this analysis again, because this is quite important. Each time you make a comparison, okay, an element of C gets filled. So if I make k comparisons, then I fill k elements in C. The total number of elements in C is n, right? So the number of comparisons I make must also be bounded by n. Good. So the total number of comparisons is n. Okay. The reason is, for each comparison, we add an element to call this array C. Okay, from these two smaller arrays A and B, I pick an element and add it to C. The total number of elements in C is n. Okay, the total number of elements in C is n. So the total number of comparisons I make is also n. Okay, let's do this merge differently. So the total time now is n, we know this, and we can now write the recurrence and we'll solve it. That's fine, but let's again do this merge a bit differently. Okay. Okay, so we are now going to apply our design principles, okay, which is induction. If I can merge two smaller arrays, how do I merge larger arrays? Okay, good. So let's look at this again. So here are my two arrays. Here is C. Okay. Now, I know that the first element in C is the smaller of these two elements. Okay. The first element here is the smaller of these two elements. So let's say this is smaller. Now I look at the input without this. Okay. The input now consists of one less element from here and some elements from here. Okay. Now the sizes need not be same. So I can, supposing I solve my problem for this smaller input, can I solve the problem for the larger input? Well, the answer is, should be, vociferous yes, it can be solved, right? This is the smaller of this shaded is the smaller of these two, okay? And now I have two arrays here, so the total size is smaller. Okay, one element I have removed. So these two I merge to get this portion, and the smaller element I put here. So this goes in here, okay, and recursively I can sort of merge these two to get this portion, right? So this is the other way of doing this. Here you would naturally use recursion and not iteration, at least initially. Maybe later on you will see that this can be implemented iteratively, and you could put them together iteratively. Okay. So now how much time does this take? Okay, if there are two elements, so let's write the recurrence here. So T, so this could be n and m, okay, because they could have different sizes, right? So if it's okay, let me not use n here. Let's say m1 and m2. Okay, it's m1 and m2. Okay, T of m1, m2 is what? Well, one of them decreases by 1. We don't know which one. Okay. So maybe I can just write a recurrence on the sum of these two sizes. Okay. So I can actually write it on n. This n stands for the sum of these two sizes, which is the total number of elements in the input. Okay. This is nothing but t n minus 1 plus 1. Okay. Where does this 1 come from? This is to when I have two lists. Okay, for the first comparison I compare these two elements, remove the smaller one and apply recursion. Okay, this 1 comes for the first comparison I make, and you can check that Tn, the solution to this, so T of 2 is 1, the solution to this is Tn equals n minus 1. Okay. So to merge two arrays, the sum of whose sizes is n, the number of comparisons I make is n minus 1. Okay. So yeah, so these are two ways to do this merge. When you write the code, actually the comparisons the both algorithms do will be, if you unroll the recursion, you will actually get the iterative process back. Okay. Good. So now we can go back to merge sort and look for what's the time that we need. Okay. So it's twice Tn by 2 plus order n. Okay. So in fact, let's just put n here for simplicity. You can put a constant times n and calculate this. It will make no difference. The constant will just come out of the calculation. Okay. So now we need to solve this recurrence. I guess most of you would have hopefully do know how to solve this. Let's anyway do this. Okay. So Tn, T2 is 1. Okay. Well, I should strictly write Tn is less than equal to 2Tn by 2 plus order n. Okay. If I'm writing comparisons, for the simple reason that if I have two arrays, okay, whose let's say if they are not of equal size, then I could use less than n. In this case, it is n and it's equal, but often you should sort of check whether this should be equal to or less than equal to. In this case, it's in fact equal, and Tn is twice Tn by 2 plus n. Okay, so this then is so let's open this out. Okay, twice T n by 2 squared, right, plus n plus n. So this T n by 2 I have replaced. I have again used this recurrence. I'm sorry. So this should be n by 2. Okay, I have just used recurrence. I use the same recurrence on T n by 2. So that will be twice T n by 4, right, plus n by 2. Okay, but just using this with n by 2 in place of n. Okay, so that's what I get. So what is this? This is 2 squared T n by 2 squared, right, plus n plus n. So if I do this I times, well, you could do it once more to see what the pattern looks like. If I do it I times, I get 2 to the I times T n by 2 to the I, right, you can plus, okay, there will be a number of n's. So how many times will I have n's here? It will be I times n. This you can check. If you do it once more, okay, you will get 3 times n. So here I have 2 times n. If I do it once more, I get 3 times n. The next step you get 4 times n. So you check, you sort of guess that this is what is going to be after I steps. And you can actually check this by induction on I. Once you have guessed this, you can check that Tn is in fact equal to this by induction on I. Okay, that I'll let you do. Okay, now what? Well, we continue till n by 2 to the I. Okay, so let's start here. Now we know T of n is 2 to the I times T n by 2 to the I plus I times n. Now I know T of 2 is 1, so I will let n by 2 to the I to be 2. Okay. Okay, so then what do I get? If I choose an I so that this is true, then I get Tn is, well, 2 to the I is n by 2. This is T by T of 2, which is 1, okay, plus I times n. Okay, what is I? Well, I know 2 to the I plus 1 is n, okay. So I is log base 2 of n by 2. Okay, this is what I is. So plus n times log base 2 of n by 2. Okay, this is order n log n. Okay, so the time taken by merge sort is n log n. There is one more way to do this divide and conquer business on arrays to sort, okay, and it in fact gives rise to another well-known algorithm which you may have studied. Let's see what this idea is. So here's the array. Okay, I still want to do divide and conquer. Okay, so I still want to divide the array into two parts. Okay, somehow work with each part and then put the solutions back together. But the way I do it will be slightly different in this case. So what I do is this. Okay, so what I do is in the divide part, I start rearranging the elements of the array. Okay, so I now have two parts to the array, but these are not divided as in the previous case. Remember, in the previous case we just picked up the array and just divided arbitrarily into two parts. This time we are going to be more careful. What we would like is every element landing up in the left is smaller than every element landing up in the right. Okay, so if there is an x here and a y here, I know that x is less than y. Okay, again, every element in the array must occur in one of these. So somehow I have divided this array into two parts, left and right, so that elements in the left are smaller than the elements in the right. Okay, this somehow we have done this. Now what we do is just recurs on these two parts. So you sort the left separately, you sort the right separately. Okay, let's see what happens once you do this. Once you do this, I claim that the entire array is now sorted. Why is that so? Well, this portion is sorted, right? This left portion is sorted, this right portion is sorted. I also know that every element on the left is smaller than every element on the right. Okay, so the largest element here is smaller than the smallest element here. So when I look at the entire array, you can check that the entire array is now sorted. Okay, so this is also an example of divide and conquer. The divide step is where we did work. Okay, in the divide step, which I have still to specify, you somehow divided this array into two parts, left and right. Okay, so that elements in the left are smaller than the elements in the right. This was the divide step. Now it's recursion. Okay, no sweat. You just recurse on these two parts and recursion does it for you and you sort these two. Putting things together is trivial. Okay, you just have to do no work. Both of them are sorted. When you put them together, in fact the entire array is sorted. Okay, so the only thing we need to figure out is how to divide the input so that everything on the left is smaller than everything on the right. Well, some of you may have noticed that this is an algorithm that you have seen before and it's called quicksort. Okay, again, let me sort of emphasize that earlier on you were told what these algorithms are. Okay, you were given code for quicksort and said, well, this is quicksort, that this sorts an array. Our emphasis here is to see how do people come up with these algorithms. How does somebody come up with an algorithm called quicksort? Okay, well, this is how they come up with. Okay, so you start with divide and conquer at the back of your mind, and you figure out how do you put this paradigm into place. Okay, good. So now, how do people? How do we split an array into left and right? Well, you pick a pivot. Okay, some element in the array which you call the pivot. Left consists of every element which is smaller than the pivot, and right consists of every element which is greater than or equal to the pivot. Okay. So the smallest element on the right is the pivot, and you know that in the left of the array every element is smaller than the pivot. Okay, so that does it. Okay, so let me just write this down so that we have quicksort in front of us. Okay, so pick a pivot. Okay, this is quicksort. Okay, pick a pivot, divide into two parts, smaller than the pivot, elements, let's call this P, pivot P, okay, and elements greater than equal to P. Okay, these are elements less than P and elements greater than equal to P. These are the two parts. Recurs and put them together. Okay, that's the last step. Well, unlike the difference between merge sort and quicksort is essentially this. In quicksort, this is where you spend most of your time. Okay, putting them together is easy. In merge sort, dividing it into two parts is easy. Putting them together is where you take time. Okay, so this is quicksort. Okay, how much time does quicksort take? Well, it depends on which element you pick as the pivot. Okay, so let's see what really happens. So supposing you picked the ith element. What do I mean by ith element? It means in the sorted order, it's the ith element. Okay, so let me make a definition here which we'll use later on. The rank of an element is its position in the sorted order. Okay, recall that we are assuming that each element in the array is distinct. So each element has a distinct rank. Okay, if there are I elements smaller than x, say x is an element, I elements are smaller than x, the rank is I plus 1. The minimum element has rank 1, okay, and the maximum element has rank n, which is the size of the array. So the rank of an element is its position in the array. Okay, so everything depends on the rank of the pivot. So if the rank of the pivot is I, okay, then the time taken, okay, there will be I minus 1 on one side and n minus I plus 1 on the other side, right? So is t of I minus 1 plus t n minus I plus 1, okay, plus the time taken to partition the array. What was this time? How did we partition the array? Well, we compared each element to the pivot, put the ones on the left and put the lesser ones on the left and the larger ones on the right. So we compared every element to the pivot, right? So the number of comparisons we made is n minus 1. For ease of calculation, we'll just say this is less than equal to n. Okay, it will not bother us much. What is the constant between friends? Okay, so if the rank is I, then it's at most t of I minus 1 plus t n minus I plus 1 plus n. This is the time taken to partition the array, right? Because every element was compared to the pivot once and exactly once. Good. So what is the solution to this recurrence? Clearly, sort of it depends on I. Okay, it depends on what I is, and for various values of I, it varies. Okay. For instance, if I had picked the minimum element, okay, if I had picked the minimum element, then what happens? Then I was 1, right? Oh, sorry, this should be minus 1, I guess. N minus I minus 1, or it should be n minus I plus 1. Okay, that's what sits in here. It's n minus I minus 1. Good. Okay, so if I were 1, okay, then there is nothing on the left, okay, and there are n minus 1 elements on the right hand side, right? Yeah, there's something wrong here. This should, I guess, be n minus I. There's no 1 here. Okay, this is exactly n minus I. Okay, I have the pivot. I have I minus 1 here, and I have n minus I elements on this side. Okay, the pivot sits at the center. Okay, so the right hand side has size n minus I. So if I had chosen the minimum element, then I get t of n to be t of 0, which is 0, plus t of n minus 1 plus n. And if I kept picking the minimum element as the pivot, what is this time? Okay, so let's write this again. So Tn looks to be t of n minus 1 plus n. Let's expand this further. It's n minus 2 plus n minus 1 plus n, and so on and so on. Well, it comes down to 1 plus 2 plus so on up to n. Okay, this is n times n plus 1 by 2. Okay, this is order n squared. So if the pivot turns out to be the minimum element in each case, then the total time taken is order n squared for quicksort. Okay, and you can check that if I start increasing now, let's say the pivot was the second element, then the time decreases. Okay, it will decrease till you reach the middle element. Let's see what happens if I pick roughly the middle element. Then t of n, roughly I'll have two problems of equal size. Okay, that is 2tn by 2. Okay, plus n. This doesn't change because every element I have to compare with the pivot anyway. This recurrence, I know what the solution is. Okay, this looks like order n log n. Right. So let's sort of write all this on one slide and look at it. I started out with saying, let's say Tn with Ti plus T n minus I plus n. Now if I equals 1, okay, there is I minus 1 here. Okay, if I is 1, then I get order n squared. If I is roughly n by 2, then I get order n log n. Okay. Well, one can check that if I plot Tn versus I, then it initially falls. Okay, we start with n squared. It initially starts falling till I roughly n by 2, and then again it starts rising. So if I pick the maximum, it's very similar to picking the minimum. Okay, the array size is split much the same way, and it again goes back to n squared. So the worst case time is n squared, and if you manage to pick the pivots correctly, I mean if you pick the middle element at each stage, then the time taken by quicksort is n log n. Okay, so we are only worried about the worst case time. So if somebody asks you what is the time taken by quicksort, well, it's n squared. Okay, this implementation of quicksort takes order n squared time because that's the worst case time. If somehow we could pick an element of rank n by 2 efficiently, okay, if you can pick an element of rank n by 2 efficiently, what do you mean? What do I mean by efficiently here? It means the recursion should not change much. Okay, so if I know I get n log n with the following recurrence, Tn is 2Tn by 2 plus n. In fact, I could add a constant here and it would still be n log n. Okay, this will still give me order n log n. Okay, you can check this. This constant will just come out of the calculation. Okay, if I have Cn, then I get n log n. Now, if I can somehow find the middle element of an array, which means an element of rank roughly n by 2. If I can find an element of rank n by 2 in constant times n time, then I can implement quicksort to take time order n log n. The way I do it is I first I spend Cn time, pick this middle element, the element of rank roughly n by 2. Now I do the usual, okay, use this pivot, divide the array into two parts, and now the array is divided into two roughly equal parts. Once I divide them into equal parts, now it's the usual recursion and I'm done. So I take n log n time. So I can implement quicksort. There is an implementation of quicksort. There will be an implementation of quicksort which takes n log n time, provided I can find this element of rank n by 2 in linear time. Okay, which is what we do next. Before we do that, let me point this fact out, that in the recurrence, it was desirable that the two parts were of roughly equal size. If they were not of equal size, then the time was proportionally, it was higher, right? So often in these divide and conquer kind of situations, we try and see if we can somehow split the input into exactly two parts, into halves. So once we have halves, because of the way these recurrences work, the time taken is usually smaller. So our job next is to figure out how to pick this element of rank n by 2 in linear time. Okay, so let me state this problem. Okay, so this element of rank n by 2 is called the median. So the median is an element of rank n by 2, let's say floor of n by 2. You could take the ceiling of n by 2, it doesn't matter. Okay, so if n is odd, you take the floor of n by 2. And our job, okay, so what we want to do is this. So the algorithmic problem, given an array, find the median. So how do you find this element of rank roughly n by 2? Well, the easy way to do it is sort the array and pick the middle element. That takes time n log n. Right? The time for that is n log n. So if we, for instance, use merge sort, that is not good enough. Can we do it faster? The answer is yes. Okay, you can in fact do it, find median in linear time, and this will be the first non-trivial algorithm that you will see. It's a really smart algorithm, and as we present, I hope you appreciate the beauty of this solution.